So the disaster recovery is always quite a debated task and a hot topic in companies. And there are different approaches that one could take regarding this topic. In particular, one could just say, well, we'll never have a disaster, so why should we care about that? Or we could even plan a bigger disaster and just to let our own disaster become irrelevant. But talking more seriously, when we speak about Vault, it is quite central piece in our infrastructure, in the IT infrastructure. So it's nice to have a disaster recovery plan in case indeed of a disaster. So we'll just quickly go through a basic architecture. And here we are leveraging the HashiCorp Vault Enterprise license. So we have access to the disaster recovery of Vault. So let's see. We start here with a Vault cluster, which is for 5 EC2 instances behind an auto-scaling group, and everything is behind a network load balancer. Now, it makes sense to create an endpoint, a Route 53 endpoint for this network load balancer. In case if it will be destroyed, we can just have this kind of endpoint, which we call, for example, vault-primary.company.abc. Now, this constitutes our primary cluster, and it will then have also a higher level endpoint, another Route 53, CNAME or alias, which we call vault.company.abc, which will be used by users to interact with our primary cluster Vault. Now, leveraging the enterprise license, we have another cluster, complete replication of the primary. Its endpoint will be defined as, for example, vault-dr.company.abc, and the data will be clearly in sync between those two clusters. Now, if the primary goes down, alerts will come in, and everything will be kind of a disaster indeed. So we just need to see now how we could recover from that. So the procedure in case of a disaster for a Vault cluster is to, first of all, promote the secondary to a new primary. Now, this process involves the use of recovery keys or to use a DR operation token. Clearly, this token needs to be created before. And then after that, considering the architecture that we saw before, we also need to change the Route 53 records to point to this new primary. Now, this is slow and error prone. Also, when talking about Route 53 records changing, we can incur in some caching problem. So, what we are going to talk in this presentation, first of all, we are going to go through the workflow that we designed at YNAP to overcome these issues using AWS Lambda functions. We'll go into more details regarding the design of these functions, and finally, we will inspect the repos that we use to construct all of this infrastructure. Hello, I'm Kevin. I'm a DevOps engineer at UX Net-a-Porter Group. On this slide, you can find some of my online presence. If you want to contact me, please be my guest and drop a message. So let's go through. We'll start with the high-level introduction and architecture. Then we'll go through the design of the AWS Lambda functions. Then afterwards, we'll go in depth for a more in-depth analysis of the solution, and then we'll draw some conclusion. So let's start. This is the picture that we saw before of the architecture. To overcome the DNS issues, the caching problems, we just created a weighted policy. So in Route 53, you have the possibility to create DNS routing policies. And so for our high-level domains, this vault.company.abc, we pointed it to both the clusters, and we set the weight for the primary cluster to be the maximum weight, so 255, and the weight for the secondary cluster to be the minimum one, namely 0. In this way, all the traffic will be redirected to the primary and not to the secondary. Now, let's see, in case of a disaster, what is our workflow. So, disaster happens, an IT human is triggered, and we'll start with the first Lambda in our picture, which we will call the DR operations Lambda. So the IT human will invoke this Lambda, and this one will retrieve the DR operation token. So this is the token that is needed to interact with the secondary cluster, to promote it, and to eventually demote the primary cluster. Now, this DR operation token will be put in secrets manager by another Lambda, which we'll call the DR operation token gen Lambda. And finally, once the DR operations Lambda has taken this DR operation token, it will be able to promote the secondary cluster to a new primary. After that, we will invoke another Lambda, which we'll call the DNS switch. And what it will do is just to swap the weights of the Route 53 DNS records. So it will put to 0 the old primary and put the maximum value for the new primary cluster. Now, I'd like to demonstrate these concepts in a quick demo, and we'll see how these two scripts will be used and will indeed make all these changes in the primary cluster and the DNS. So we can see here that we have our primary cluster, vault-primary.hashiconf.demo, and there's the login screen. Then we have our secondary cluster, which is in replication mode, vault-dr.hashiconf.demo, and that we have our higher level endpoint, which will point to the primary cluster. Now we can go to our bash terminals. We have two terminals here, the first for the promotion and demotion, and the second to the DNS switch. So in the first terminal, we can launch the promotion and demotion script, and we can start the timer here. So it will check the primary endpoint and the secondary. It will demote the primary, promote the secondary, and it will link them together. So now we can go back to the Chrome tabs, and we can see here that the primary is the secondary, and the old secondary is now a primary. So we can now go to the DNS switch part and deploy it, and this will change the DNS weights. So it will allow the endpoint, the higher level endpoint, to point to the right one. Now here we have some caching from the browser, so we just clear the Chrome from the DNS caching. We refresh, and here we have the new primary. So our endpoint points to the new primary, which was the old secondary. And all of that took less than a minute. So let's now dive into the design of these AWS Lambda functions. So first of all, let's look at the general architecture that we have. We have a central Lambda, which we'll call Auth Lambda. This Lambda will be in charge of authenticating to HashiCorp Vault and return a token to the other Lambdas. So the step 0 for the other Lambdas is to invoke this auth function. This will indeed authenticate to Vault using the roles passed as payload. It will get the token, it will return the token to the Lambdas, and then all these Lambdas will be able to interact with Vault. So in our story here for the disaster recovery plan, we have 4 Lambdas. The AWS Auth Lambda, the DR operation token gen Lambda, the DR operations, and the DNS switch. So let's inspect all of these one by one. So let's start with the first. So this Lambda will first of all take as an input the AWS Auth method role from the calling Lambda. Then it will sign the payload using the AWS STS service. It will make a request to Vault to authenticate, and then it will return the token. So the calling Lambda will be able to interact with HashiCorp Vault. Now let's see a graph. So we have our auth Lambda, which will be invoked by another function, passing the role as a payload. Now this Lambda will sign the payload using the AWS STS service. It will make post request to the /auth/AWS/login endpoint of our Vault cluster, and then Vault will return a token. After that, the auth lambda will be able to return the payload to the calling lambda. Now we can inspect the DR operation token gen lambda. This lambda is in charge of generating the DR operation token and uploading it to Secrets Manager. So first of all, it is scheduled every 8 hours using CloudWatch events. And as the DR operation token itself will have 8 hours of TTL, then it will invoke the AWS auth lambda, so the previous lambda, to get a Vault token, since it needs to interact with Vault. After that, it will make the request against Vault to get this DR operation token. And finally, it will upload these tokens to Secrets Manager. Now, once the token is there, it can be used by other lambdas or by anyone else. So it will be available in case of a disaster. So let's see a picture of it. We have our DR operation lambda, DR operation token gen lambda, which is scheduled every 8 hours by using a CloudWatch event. Now this lambda calls the auth lambda, which itself will authenticate to Vault, get a token, and return a token to our initial lambda. Now it will be in this way it can request a DR operation token to Vault, since it is authenticated, and then Vault will return this token. Afterwards, our DR operation token gen lambda will be able to upload or refresh the DR operation token in Secrets Manager. Let's now take a look at the DR operations lambda. Now, this lambda is in charge of promotion, demotion, and linking of the Vault clusters. So, first of all, it will infer which endpoint is the real primary and which is the secondary. So as we saw before, we have the kind of second layer endpoints, which is Vault-primary or Vault-dr, but the name does not reflect always what is actually the primary and the secondary. So first it will infer which is the real primary. Then it will retrieve the DR operation token from Secrets Manager. After that, it will try to demote the primary. Clearly, in case of a disaster, it will not be able to do that, but it will go through anyway. And then it will promote the secondary. So the important thing is to promote the secondary in case of a disaster. After that, it will try to link the two clusters together. Clearly, in case of disaster, this will not go through, but it's okay. So let's see a picture of that. So we have our DR operations lambda, which will first retrieve the DR token. Then it will check the endpoint to see which one is the real primary. Then it will demote the primary, promote the secondary, and then try to link these two together. Now we have our final lambda, the DNS wait switch lambda. So these two, first of all, will check which endpoint is the primary or the secondary. Then it will set to 0 the wait for the real secondary, and it will set to the maximum value the wait for the real primary. So we can take now a look at the picture. So we have the DNS switch lambda function. We will check first of all if which of the cluster is the primary one, and then we will set to 0 the wait for the real secondary. So after we swapped the two primary and secondary, we can now also lower the weight for the old primary, which is now the secondary. And then we can upgrade the weight for the new primary cluster to 255, so to the maximum number. So now that we have analyzed the lambda functions from a higher level, we can go into more details, and so we can analyze the repos that we developed for our solution. So we have two repos, one with the live environments and one with the modules. So the first one is the IAC Vault-dr, and this is the repo containing the live environments. So what is deployed will be in there. We have three environments here, as you can see, the dev, the stage, and the prod clusters. And this repo will reference the modules, the module repo, which is the other one, the Terraform-Vault-dr. And here we will define all the code, so the Terraform code for the Lambda functions, for the vote policies, and the source code for the functions. All of this you can find in my GitHub, so if you want to take a look at these repos, please go on. If you find some bugs, some errors, please contact me, and I'll be more than happy to fix everything and to talk about that. So we can now inspect the RAC vote-dr. Here we find 3 environments: the dev, the prod, and the stage environments. We have 4 Terraform files: the backend.tf, the main.tf, the locals.tf, and the providers.tf. So if we take a look at the locals.tf, we are defining the local variables. The only one that will be different between each environment is indeed the environment one. In this case, we are inspecting the dev one. Then we have the hosted zone name, in this case HashiCorp.demo. And then we have the 3 endpoints, the higher level and the 2 lower levels endpoints. And finally, the vote address, which will be used for the vote provider. Then we can look at the main.tf. Here, as you can see, we reference the Terraform-vote-dr module. And the cool thing about that is that we can use a specific version. So for the dev cluster, we usually at YNAP take from the master branch, so we can develop our module in the master branch, then we can deploy immediately in the dev cluster, so we can see the changes. If everything is fine, we can tag this specific commit with a tag, and then we can use that tag to deploy, for example, the stage environment. Now, the stage environment is used for more in-depth tests, and then we can propagate the tag also to the prod environment. So in this case, we can see that we pass all of these variables to the modules, the environment, all the endpoints, and an identifier, which in this case is just a random ID. Now, the combination of the environment and the identifier, as we will see shortly, will be defined uniquely for each cluster and for each deployment. So we will not have any clash with the names of our deployments. Then we can see the providers.tf. Here we have just 2 providers, the AWS provider and the vote provider. And finally, we have our backend.tf file. Here we have defined the where we store the state file, in this case on an S3 bucket. And this will also differ between each environment. So this is the dev case. We have a specific that.tf state key for that cluster. Now, in this repo, we can also find a makefile and a Jenkins file. In the makefile, we define the targets that will be used in the Jenkins file to install dependencies, make some tests, and eventually deploy the cluster. So we can take a look at the makefile here. At the top, we have some variables which define the versions of the binary that we are using, and then we have some targets. So if you want to take a look, you can go to the repos on my GitHub. You can see the code, and in particular here we have some targets for installing the dependencies, Terraform, Chekhov, and other things. So you can just see that. Finally, we have the test target, test-Chekhov, and Chekhov is a tool for making tests on the code, so the Terraform code, to make it compliant with some best practices. So here we make also this test. And finally, we have the deployment targets, let's say. So we have all the Terraform init, plan, apply, and eventually destroy. And we have the environment variable, which will define where we are actually deploying. So if we want to deploy in dev, in stage, or in prod. Now, the Jenkins file here is an example. Here we use a declarative pipeline. We define everything to be run inside a Docker container, and the image is just a custom image. It's a CentOS my CentOS. This is also one that I created for the purpose of this demo, and you can also find this on my GitHub. And there are some stages and a post action. Now, the stages, in this case, the first 2 stages are common. So here we are using a GitOps approach. So the first two stages will be run in both commits, pull request, merging. And the first is to gather the vote tokens. So you manually put a vote token to interact with the cluster. Actually, we at YNAP, we avoid to put manually the token since we leverage the AWS auth method, but for the purpose of this demo, I just placed this stage to just insert manually the token to deploy resources into the vote clusters. Then we have a stage for install the dependencies, and then we have the stage that runs the test. This stage, which is the third one, will be run when we are committing on a branch that is not master. And then we have the Terraform plan, and this plan will be run when we are making a pull request. And finally, the Terraform apply will be run only when we are merging to master. Finally, we have a post actions that will be run always, which is the removal of some Terraform resources. Now, this is needed as we are running the container using root privileges, which is not really a good practice, but it's always for the for the demo, it's okay. And we needed to remove some Terraform resources that are created as root, so that Jenkins in subsequent runs, if you were not to delete these resources, Jenkins will not be able to delete them, as Jenkins run as a Jenkins user and the resources are created as root. So we need that stage. Now we can see here the pipeline. So when we push to a branch, we gather the tokens, we install dependencies, and we run some tests. In this way, right now, just only the checkoff test, so we can see 44 resources passed. Then we make a pull request. Also, the plan is triggered, and we see here 44 resources to be added. And then on a merge to master, only the deployment part is run. In this case, 44 resources added. So we can now inspect the module repo, so the Terraform-vote-dr repo. Here we can find Makefile, Jenkins file, and a Terraform folder. In this folder, we can find all the definition for the Lambda functions, the vote auth methods, policies, and also the source folder, the SRC folder, which will contain the code for the Lambdas themselves. As we can see here, we have 3 Lambdas written in Node.js and 1 written in Python. So that's the cool thing about Lambdas. We can write the code in whatever language Lambda supports, so without any problems. And the Makefile will contain the installation of Golang, which we will use to make some Terra tests, and the installation of Terraform and Node.js. And then we have a target to indeed make the tests, which are contained in the test folder. The test folder, as we can see, has an example folder and a main_test.go file, which will contain the Terra test. Now, the example is kind of a mock of the environments, so it will make use of the Terraform module here. And the Terra test the Go file will just create, make a Terraform init plan and apply of the cluster, and then it will destroy it. So as we can see here, the Jenkins pipeline will just gather the vote token, will install dependencies, and will run the tests. In the test here, we can see that we have 2 passed tests, which is one, the creation of all the resources, and one for the destruction. Clearly, one should put more tests in the Go file, but always for the purpose of this demo, this is okay. So if we go back to our resources, our Terraform resources, we can just inspect our module. So let's see first of all the inputs of our Terraform module, which is the environment, the vote endpoint, the endpoint of the primary, the endpoint of the secondary cluster. Then we have the hosted zone name, and then we have the identifier. Now this module will produce our 4 Lambda functions that we saw before, with also all the resources around them, and it will also deploy the vote policies needed and the auth methods roles on both. Now, Every resource will have its own unique name as the resource name -environment-identifier. Now we can take a quick look at locals.tf. Here we just have 3 variables, the unique ID, which is the combination of the environment and the identifier, and then we have the name of the operation token and the role name. Now, looking at the code for the AWS Lambda, here we have our module. We make use of the serverless.tf Lambda module, which is a cool module to deploy Lambdas, and we have defined the function name like that, and the runtime is Node.js. We make use here of the source path, and we point to the source that we saw before. And as an environment variable, we just have the vault endpoint. Now, for the other lambdas, I will not go through the code as there is no time for that, but you can look at the GitHub. So here are the resources that are needed, for example, for the DNS switch. And here are the environment variables that it needs to deploy correctly this switching mechanism. Then we have our DR operation token gen lambda that it will need the secrets manager access to put the new secret value, and then invoke the auth lambda. It will also contain the scheduled trigger, the CloudWatch trigger, and the creation of the secrets in the AWS Secrets Manager. And these are all the environment variables that this lambda needs. Finally, we have the DR operations lambda. Now, this lambda will need access to the secret, so it needs to have these permissions for secrets manager, and it will need clearly these environment variables to being able to make the promotion and demotion operations. Now we can take a quick look at the policies. So in the Terraform-vault-tr, we can see here that there is a vault_policies.tf. And first of all, we have the policies taken by the DR operation token itself, and it will have access to the /dr/star path to make all the promotion, demotion, linking, etc., with the capabilities to do everything. So that's our token. Then we have the token that will be given by the auth lambda when it authenticates Vault, and this token will just need to being able to create the DR operation token. So this is the path that it needs, and as the capabilities will have the update and the create one. Now, the authentication method, as we can see in the module, there is a vault_auth methods, auth backends.tf, and it will contain the roles for the backends. So the first is for the DR operation token, that will be a batch token, and a batch token is always orphan and not renewable, so maybe these 2 attributes are not necessary, but just put in there. And we reference the policy that we created before. Then we have the auth method, the AWS auth method role, which we make use of the data source to make sure that the backend is mounted. And then we define the token TTL to be 5 minutes and 10 minutes stop. And we use the AWS as the we bound the IAM role of the Lambda, of the AWS auth Lambda that we created before. The source code, I do not have time to actually go into more details on that, but you can check the code, please. You should do that, and you can just message me to, if there is any problem, I will be more than happy to go through it. So let's just draw some conclusions here. So we have defined 4 Lambda functions and 2 repos in a GitOps approach and 3 environments, and all of this allows us to come to a sub-minute recovery time of the Vault clusters in case of a disaster. Also, as a scalability, we can use this AWS auth Lambda function for other Lambdas. For example, we can use it for a crawler. So if we want to crawl the Vault, we can use it to create a specific token for that to be used, or to create a Lambda to move secrets around, even between clusters, or whatever else. These are some use cases. And also we can use this procedural promotion and demotion to upgrade the clusters. So we can upgrade the secondary cluster, then we can swap primary with secondary. We upgrade the old primary, which is now a secondary one, And then we can swap again. In this way, we have minimized the downtime, and if some errors occur, they are always on the secondary side. So these are some use cases. I hope you enjoyed it, and thank you for your time. Here there are some links if you want to contact me and to check the repos. Thank you.